Right now, something's drifting through our solar system that just shouldn't be here. The math says no. The physics says no. All the tidy models we've built up, all the rules that have always explained every comet, every icy rock that's ever wandered into our view, they're all coming up empty. And the people who are supposed to have answers, the ones with access to billion-dollar telescopes and endless streams of data, they're losing sleep. Because this thing, 3IATLAS, an interstellar visitor straight out of the darkness between stars, is breaking rules comets aren't supposed to break. And if you're NASA, if your whole reputation hangs on being able to make sense of what's out there, an object like this is more than an oddity. It's trouble. The kind of trouble that keeps top scientists awake at night, staring at screens full of stubborn data, running calculations that refuse to add up, and quietly wondering if they've missed something big. The discovery didn't come with any fireworks. No eureka moment. Just a quiet blip in the data, the way these things usually start. July 1st, 2025, a telescope down in Chile, part of the Atlas network, picked up a faint smudge of light slipping past the usual background stars. The machines noticed first, not people. The software did what it always does, flagged the blip, logged it, filed it away with thousands of other dots, and sent off the coordinates for someone to check later once the urgent asteroid tracking was done. Just another ordinary bit of cosmic debris, another number in a database, but this one wasn't moving like it should. Its path didn't fit anything orbiting the sun. It was going way too fast at the wrong angle, slicing through the solar system's plane in a way that said, "I'm not from around here." When the computers finished crunching the numbers, the answer came back clear. This was a hyperbolic orbit. It's not tied to our sun. It's not one of ours. No ambiguity, no debate. This thing came from deep interstellar space, traveling for who knows how long, until a nudge from gravity sent it sailing through our solar system. A one-time visitor, never to return. 3IATLAS. The name spells it out. The third confirmed interstellar object we've ever spotted after Oumuamua in 2017 and 2I/Borisov in 2019. The I stands for interstellar. Atlas is the telescope network that caught it. By the time everyone scrambled and pointed their biggest instruments at this cosmic drifter, it was already cruising through our solar system, headed toward the sun, set to slingshot back out into the galaxy and vanish forever. This was it. A chance to study something born around another star, a frozen time capsule from a place we'll never visit, shaped by conditions we can only guess at, carrying secrets written in ancient ice and rock, drifting across light years for millions, maybe billions of years. The scientific world kicked into high gear, the kind of scramble you see for supernovae or gamma-ray bursts. Hubble turned its gaze. James Webb zoomed in with its infrared sensors. Observatories from all over the world joined forces, sharing every scrap of data they could get, racing to capture as much as possible before the visitor slipped away. It's the sort of moment that comes once in a generation, if you're lucky. Then the data started pouring in, and honestly, none of it made sense. Not right away. There wasn't some dramatic, world-ending discovery that sent everyone scrambling, but observation by observation, things just got weirder. At first, the differences looked small, stuff you could blame on a glitchy instrument or a calibration slip. But the weirdness stuck around. It showed up on different telescopes, using different methods with different teams. After a while, no matter how much anyone tried to shrug it off, it was obvious. 3IATLAS wasn't going to play by the usual rules. Comets are supposed to be easy. We call them dirty snowballs, and honestly, it fits chunks of ice and rock, leftovers from when the solar system was just getting started, frozen solid far from the sun. Sometimes gravity nudges one inward, sunlight hits, and everything changes. The ice skips straight to gas, venting into space. You get those wild tails, bright and beautiful, stretching across the sky. We've seen it all before, and we've kept records for centuries. We know what to expect. We know what comets do, what they're made of, how they break apart, how they change every time they swing by the sun. In astronomy, comets are about as close as it gets to something we genuinely understand. But 3IATLAS didn't care about any of that. It was off script from the start. The first hint came from the chemical fingerprints in the spectroscopic data, the stuff that's supposed to tell you, without a doubt, what elements and molecules you're looking at. Split a comet's light into a spectrum and you get a barcode of its chemistry. Water shows up here, carbon dioxide there, dust somewhere else. Usually, water's the big player. It's always been the main ingredient because way out where comets form, water ice is just everywhere. That's been true of every comet we've really studied. But this one, 3IATLAS, threw that rulebook out the window. Its spectrum looked so strange that the scientists checking it had to stop and wonder if their gear was broken. But it was. Carbon dioxide didn't just show up, it dominated. The ratio was so off the charts, so far from anything in the solar system, that some people just assumed it had to be a mistake. But it was. The James Webb Space Telescope backed it up, clear as day. Different instruments, different methods, all saying the same thing. This comet's coma, the glowing cloud around its core, was blasting out carbon dioxide like nothing we'd ever seen. Water was still there, sure, showing up where it should, but it was barely a supporting act in a show where it should have been the star. That chemical fingerprint didn't just hint at something odd, it shouted it. This wasn't anything our solar system cooked up. We were looking at material shaped in a place where carbon dioxide ice could actually stick around, pile up, and survive, unlike anything that ever happened here when our planets were forming. Alien chemistry in the truest sense. Not little green men, not some distant biology, but the bones and skin of worlds built under rules we've never really seen in action. Imagine a protoplanetary disk with totally different temperatures, with carbon and oxygen mixed in weird new ratios, with ices freezing and melting in a sequence that just doesn't happen around our sun. All of that changes what kind of ices can exist and where you'll find them. And 3IATLAS, well, its makeup was like a postcard from a nursery where stars and planets play by different rules. That was exciting. That was good science. That's exactly why we want to catch interstellar visitors in the first place. But honestly, this was just the start. The odd chemistry was just the first crack in the wall. The real mysteries went deeper. They had to do with structure, behavior, and motion, stuff you can't just see with a spectrum. Comets are a mess. They're chaotic, never quite predictable, even if you know the broad strokes. They break up under heat, snap and fracture as temperatures shift, and drop debris that leaves dusty trails along their paths. Their comas, a sort of fuzzy atmosphere, get lumpy and uneven, with jets of gas and dust shooting from hot spots on their spinning surfaces, lighting up in weird patches as the comet rotates. It's like watching geysers erupt on a spinning ball of ice. The tails, they whip and twist, shaped by the solar wind and sunlight, turning into tangled, beautiful chaos. Nothing about a comet is tidy or balanced. They're just loose bundles of ice and rock, barely sticking together, full of cracks and empty spaces, constantly shedding material whenever they swing near the sun. They're doomed, falling apart a little more with every trip around the solar system, peeling away layer by layer, like an ice sculpture left in the sun. That's what comets do. That's what they've always done. But then the high-res images of 3IATLAS started coming in. All the big telescopes and fancy image processors got to work, zoomed in, and immediately people were double-checking for mistakes. The coma wasn't bumpy or patchy. Actually, it was weirdly smooth, almost too perfect. Just a glowing spherical cloud around what should have been a lumpy, leaking core. No jets, no uneven bright spots or shadows, no shifting patches as the surface spun into sunlight. None of that wild, unpredictable mess you expect from a comet. Just calm, eerie symmetry. It didn't add up. And then polarimetric studies, polarimetry, which tells you how light gets polarized when it bounces off dust and ice, made it even stranger. This technique is great for figuring out what the dust is made of, how big the grains are, and how they're shaped. Normally, when sunlight hits a comet, it scatters and some of it gets polarized, letting scientists read details about the particles floating around. Every comet and asteroid we've checked shows the same basic polarization pattern. The dust and ice scatter light in ways we can predict, creating a signature you can recognize. It's so reliable that scientists use it to ID different types of objects. But 3IATLAS, it just didn't fit the script. 3IATLAS's polarization signature just didn't fit. It landed way outside anything astronomers had seen before. When they measured the light, the way it polarized at certain angles between the sun, the object, and us, the negative polarization branch was both sharper and deeper than anything on record. The data was solid, the error bars tiny. Different teams checked the numbers. Same results. This wasn't a glitch or a weird blip from the instruments. It was real, and honestly, it wasn't just rare. It was one of a kind. The researchers who published the findings, people who'd spent decades fine-tuning their polarimetry skills, kept their language measured and neutral, like scientists do when they're starring down something that breaks the rules. But you could feel the tension in their words, like a question left hanging. Whatever was on the surface of 3IATLAS, or maybe floating around it as dust, was bouncing light in ways that just don't line up with anything else we know. Not with anything in the solar system, not in the asteroid belt, not even in the distant Kuiper belt. Nowhere. So, what was going on? The particles were the wrong shape for any formation mechanism we've seen, or the sizes didn't fit with how we know dust clumps together. Maybe the stuff was made of some material that acts differently with light, something the standard comet models never included. Or maybe it was a mix of all of that. Every time someone came up with a possible answer, it just opened up more questions. It started to feel like 3IATLAS wasn't just from another star, but from a whole different playbook. A place with chemistry and physics so unlike ours that even the basics, like how dust reflects sunlight, just don't match. Then came the activity profile, and that was another curveball. Normally, comets start waking up as they get close to the sun. The exact distance depends on what they're made of, different ices, different thresholds. Water ice, which is everywhere in comets, only starts to sublimate once you're closer than about 3 astronomical units from the sun. That's around where the asteroid belt sits. Go farther out and water just stays frozen. CO2 can be active a little farther away, maybe out to 10 or 12 AU, depending on how the ice is packed in the nucleus and how much warmth it gets. But there's a hard limit. The sun only puts out so much energy, and eventually, it just isn't enough to keep things going. But 3IATLAS was showing clear signs of activity way out beyond those distances, where it was supposed to be stone cold and quiet. Ultraviolet telescopes picked up signals from hydroxyl, a product you get when sunlight breaks apart water vapor. Thing is, this was happening so far from the sun that the light shouldn't have been strong enough to make water ice sublimate in the first place. Yet there it was, spitting out water molecules and breaking them apart, leaving a signal no one expected. Not out there, not at that strength. The calculations just didn't add up. No matter how you crunched the numbers, there wasn't enough solar energy to explain what was happening. Something didn't fit. Scientists tossed around all sorts of explanations. Each one sounded reasonable enough on its own. Maybe the nucleus was just really dark, sucking up sunlight instead of bouncing it away like most comets do. A darker surface heats up more, so even out in the cold, it could still kick off sublimation. Or maybe there were pockets of supervolatile ices hiding under the surface, stuff like carbon monoxide or methane that turns to gas at temperatures where water and carbon dioxide stay solid. Those could leak out through cracks or vents, creating activity even when the sun's barely warming things up. Then there's the idea that the comet's rotation helped, spinning fresh ice into the sun's spotlight long enough to boost outgassing, even if the overall energy was low. They all make sense on paper, but every one of these explanations means tweaking the model, adding another assumption here, a new variable there, adjusting parameters to make the numbers fit. And honestly, when you keep piling on extra assumptions just to force the theory to match the data, you start to wonder if you're missing something big. Are you actually explaining what's going on, or just making excuses for a theory that's out of step with reality? And then there's the mess with the size estimates. They were all over the map, which really screws with calculations that need precise numbers. Measuring a comet's nucleus isn't easy. You're trying to pin down the size of a solid core hidden inside a glowing cloud of gas and dust. The light you see through a telescope comes from both the nucleus reflecting sunlight and the coma scattering and emitting its own. If you don't separate those right, your size estimate is toast. For 3IATLAS, people came up with everything from 440 meters to 5.6 kilometers. That's not a minor uncertainty. That's the difference between a skyscraper and a mountain. And it changes everything. Mass, surface area, how fast it heats up or cools down. All the stuff you actually need to know to understand what this object's doing. And once you start crunching the numbers, the headaches really begin. If the nucleus is small, towards the bottom of those estimates, then the outgassing rate per square meter has to be insanely high. Almost every bit of the surface would need to be venting gas, and at rates that stretch the limits of what's even possible for something just sitting in sunlight. That means the nucleus is nearly pure ice, with hardly any rock mixed in, which doesn't fit with how we think comets form. But if the nucleus is huge, up at the top end, suddenly the energy budget makes more sense. The surface is big enough to spread out the activity, the numbers look more reasonable. But then you're talking about a massive object that somehow survived ejection from its home system, drifted through interstellar space for ages, and braved all the stresses of passing near our sun, without falling apart. And now, against all odds, it's venting gas without breaking up. Either way, the story doesn't add up easily. Every path you take leads to a new set of problems with no simple fix. By the time 3IATLAS swung in close to the sun on October 30th, 2025, the whole astronomy world was buzzing. This wasn't the usual routine. People everywhere were hooked. Big observatories tracked it, working together like clockwork. Meanwhile, amateur astronomers aimed backyard scopes at the sky, snapping pictures and sharing them online within hours. Citizen scientists joined in, writing code, crunching photometry, comparing data from different spots and wavelengths. It was a wild, sprawling group effort, the kind that just couldn't have happened back before the internet tied everyone together. Now, the tools were in everyone's hands. The data was out there for anyone, and that changed everything. Then things got weird in a way nobody expected, sparking arguments that honestly would drag on for months. Professional observatories with their fancy instruments and strict quality checks were turning out images that looked exactly like you'd expect. A faint, fuzzy comet, a coma, maybe the start of a tale. Nothing shocking. But in the amateur community, something else was brewing, something that messed with the whole idea of who actually sees what's real and who might be missing it. Paul Craigs, a sharp-eyed astrophotographer with a Dwarf 3 telescope, gear that costs less than a single pro-grade detector, snapped a shot of 3IATLAS that just didn't line up with the official views. While Hubble showed mist and blur, Craig's image was the opposite. A blinding white core with crisp edges, a shape that was weirdly smooth and geometric. There was a blue glow, too, wrapped around the whole thing like some kind of energy field or maybe exhaust, like it was giving off something, not just bouncing sunlight. The photo looked too sharp, almost artificial, not what a comet's supposed to be. Comets are messy, wild chunks of ice and dust tumbling through space. But here was this image, way too clean, challenging everything we thought we knew. He posted it online and anyone could see it, a challenge staring everyone in the face. Skeptics jumped in right away, and honestly, you couldn't blame them. They called it overprocessing, said the image was juiced up until it showed things that weren't really there. Maybe stacking all those exposures created fake patterns. Or sensor noise got mistaken for real features. Earth's atmosphere twists and bends starlight in all kinds of weird ways. These are real problems in amateur astrophotography. Backyard telescopes have gotten impressive, sure, but they're no Hubble. They don't have the same careful calibration, the same control over errors. It's easy to create artifacts when you're stacking 100 frames and tweaking every setting to show faint details. And the human brain, it's a pattern machine. We see order and meaning everywhere, even when it's not real. Faces in clouds, animals in rocks, spaceships in blurry comet shots. Pareidolia is a powerful thing. So yeah, the skepticism made sense. Science needs hard proof, repeatable results, careful checking before anyone buys into a wild new claim. But then the story twisted. Other people started seeing the same thing. Different telescopes, different places, different software, yet their images lined up. The object looked too neat, too regular, too sharp to be just another chaotic comet. That strange blue glow turned up again, over and over. Not in every shot. The angle between the sun, the comet, and Earth mattered. But it showed up enough that calling it a fluke started to feel like a stretch. The doubts got harder to hold on to. People started asking questions they never thought they'd have to ask. Some researchers started taking amateur data more seriously, not for paper, not in any official way where their names might get tied to some wild claim. They did it quietly behind the scenes, late at night after their day jobs. They ran their own analyses, using professional techniques on those amateur images, just trying to figure out what the hell was going on. Instead of clearing things up, they found themselves with even more questions. Some of the structures in the images lined up with real patterns, little connections in brightness that couldn't be chalked up to noise or bad processing. But these features were faint, hard to pin down, the sort of thing you could debate forever and never agree on. So the data just floated in this weird space, too interesting to ignore but way too shaky to rely on. NASA, on the other hand, stuck to its script. Nothing changed, no cracks in the wall. For them, 3IATLAS was a comet. A weird one, sure, strange composition, odd behavior worth studying, but still natural, no sign of anything artificial. Radio telescopes heard nothing but static, no strange signals. The orbit looked fine, any wobbles could be explained by jets of gas shooting out as the comet's ice boiled off. No geometric shapes or hard edges, nothing that screamed technology. Their public statements hit all the right notes, careful, precise, checked by people trained to say just enough and not a word more. But behind closed doors, in emails nobody else would ever see, in those late-night chats after the conference talks ended, the mood was different. Not panic. Scientists don't panic, they're trained not to. But a kind of quiet worry crept in. They saw gaps between what they observed and what they could explain. One weird thing here, another there, each one, on its own, easy enough to brush off. But put them all together and it started to feel like maybe they were missing something big. Like maybe their usual ways of thinking just weren't enough for this. The orbit really got to some people, especially the ones who spent their lives working out how things move in space. Comets don't fly straight after swinging close to the sun. They just can't. Outgassing turns them into tiny, unpredictable rockets. Gas jets push on the nucleus. The direction changes depending on how the comet spins, where the jets are, which part faces the sun. All that makes the orbit messy. You have to track it, update the math, track it again, update again. Eventually, with enough data, you can predict where it'll go, but there's always some scatter, always a bit of chaos. But 3IATLAS, after perihelion, it didn't scatter the way it should have. The orbit was almost too clean, tighter than the models said it should be. For something spewing gas in all directions, it sure looked like it was staying on track. Like maybe, just maybe, something was quietly steering it. Nobody used that word, controlled, in any official papers. But in private emails between people who trusted each other, it came up. You'd see it in blog posts from independent researchers who dove into the public data, connecting dots the official reports left untouched. You'd see it in forum threads, where amateurs and professionals swapped notes and wild theories, free from the rules of formal science. When you plot the trajectory and run the simulations, tweaking the outgassing rates, factoring in the rotation period, plugging in all the gravitational pulls from the sun and planets, and folding in what the spectroscopic data actually shows, you'd expect a messier picture. But the differences between where the models said the object should be and where it actually turned up, they were smaller than you'd think. Not dramatically, not in your face weird, but just consistently off. Every time we checked, across different observation windows, the numbers lined up more closely than random outgassing from a spinning icy hunk should allow. It wasn't a smoking gun. It wasn't proof of anything wild. Still, it was there, a whisper that maybe this object was behaving with a little more order than nature usually hands out. Then there was the blackout at perihelion, those missing hours that came up in every conversation about 3IATLAS, solar conjunction. That's when Earth, the Sun, and 3IATLAS fall into a near-perfect line, the Sun smack in the middle, blocking our view. For those crucial hours, our telescopes were useless. Sunlight flooded the detectors. Scattered glare made it impossible to see anything sensitive, and the sun's radio noise drowned out any faint signals. For about 40 to 60 hours, depending who you asked and what instruments they were using, 3I/Atlas slipped behind the sun's glare. We lost it. No tracking, no data. Just a blank. Then it came back. Telescopes locked on, the trackers crunched the numbers, and right away we could see something was off. Its speed had ticked up a bit. The path had shifted just enough for anyone paying close attention to notice. Not huge, but real. A measurable change, not just some rounding error. In astronomical jargon, it was a non-gravitational acceleration event. Basically, the object had sped up in a way gravity alone couldn't explain. Comets pull this kind of stunt all the time. It's in the manual. When a comet swings close to the sun at perihelion, the heat fires up the ice, blasting gas out into space. Those jets shove the nucleus around like mini thrusters. Orbits get tweaked. Standard stuff. Nobody blinks. But for some of the researchers, the timing felt off. The acceleration happened right in the blackout, that stretch where we couldn't watch it. And when you mapped the direction of the speed-up, it nudged the object's path toward Jupiter, tightening the encounter. So precise it almost seemed intentional if you let your mind drift that way. Coincidence? Almost definitely. Of course, solar heating peaks at perihelion. That's just how orbits work. Perihelion lines up with conjunction because of how everything moves. It's the same clockwork that governs the whole solar system, but people can't help hunting for patterns. And when the odd composition stacks up with the smooth coma, when the amateur images look too clean, when the trajectory sharpens and the acceleration times itself perfectly with the data blackout, it gets harder to shrug it all off. Each little anomaly, sure, you can explain away, but all of them together, that's when doubt starts creeping in, and even the most skeptical minds begin to squirm. NASA scientists learn to be skeptics. They need evidence, hard, reproducible proof, before they're willing to believe anything out of the ordinary. That's not just a rule, it's almost a reflex by the time they're out of grad school. The whole scientific method runs on doubt. If you make a claim, you'd better back it up with data that anyone else can check and get the same result. So by those strict rules, there wasn't really any reason to think 3IATLAS was anything but a weird comet. Sure, the data pushed the boundaries of what comet physics could explain. The models bent a little, but they didn't break. Nothing in the numbers screamed out for aliens or technology, just unusual but still natural behavior. The official report stuck to that line. The peer-reviewed papers called 3IATLAS an interstellar comet noted the strange composition, pointed out the odd shapes. Every word got picked apart for accuracy. They threw in all the right caveats, as scientists do. The method demands caution. Don't let yourself get carried away by surprises in the data. But under all that careful language, under the polished analysis, there was something else. Some of the scientists, people who knew comets inside and out, people who'd spent decades tracking these icy bodies, felt uneasy. They noticed things they couldn't quite put into words, at least not in any way that would survive peer review. It was like the comet was poking holes in what they thought they knew, showing them blind spots they hadn't realized were there. One senior planetary scientist, talking quietly with colleagues at a conference, not for the record, called it the most frustrating dataset I've worked with in 30 years. And it wasn't the quality of the data. That was top-notch, some of the best ever for an object from outside the solar system. No, the problem was all the questions the data raised, questions that just wouldn't sit still, multiplying faster than anyone could answer them. Another researcher, deep in the spectroscopic analysis, wrote to a trusted friend, "Every time we think we've nailed down the composition model, a new observation comes in that doesn't quite fit and we're back to adjusting parameters." The emails and papers stayed professional, stripped of feeling, as scientists are taught. But if you knew how to listen, you could hear the frustration. This object refused to play along. It didn't fit into any of the neat categories astronomy had relied on for centuries, categories that had always worked before. Meanwhile, NASA's public face was all optimism and wonder. Press releases called it an incredible chance to study a visitor from another star. Social media buzzed with beautiful images, spectra showing off alien chemistry, reminders of how lucky we were to catch this event at all. The outreach teams talked about what 3IATLAS could teach us, how planetary systems form, how conditions vary from star to star. It was all true, and all part of NASA's job to engage and inspire. But none of that public excitement touched on the real strangeness, the little inconsistencies that kept the scientists up at night, quietly questioning everything they thought they knew. When reporters started asking about those amateur photos, images that seemed almost too organized to be random, the official answer was smooth and scientific. Sure, image processing creates weird artifacts. That's a classic issue in astrophotography. The pros use calibrated gear and strict procedures to keep errors in check. If the data hasn't been rigorously analyzed and peer-reviewed, you just can't jump to conclusions, no matter how intriguing the pictures look. On paper, it all made sense. Solid scientific process. But for a lot of people, both inside and outside the astronomy world, the whole thing felt like a dodge, a kind of polite barrier keeping anyone from asking uncomfortable questions. By late 2025, you started seeing the scientific papers hit preprint servers and journals. That's about how long it takes for research to move from raw observation to publication. There were studies on polarimetry, digging into the strange way the object scattered light. Spectroscopy work spelled out its wild carbon dioxide levels and all sorts of trace compounds. Photometry measured how its brightness shifted and how the coma evolved. Other teams focused on its orbit, trying to nail down the trajectory and the odd little nudges from non-gravitational forces. Every study added a piece to the story, every one carefully checked and peer-reviewed. And nearly all of them landed in the same place. 3IATLAS is weird, sure, but it's still a natural object, a comet from another star system, shaped by its long trip across the galaxy. There just wasn't evidence, not the kind you need for something truly extraordinary. That's where things stand now. The mainstream astronomy community backs this view, and the evidence supports it. This is a comet. An odd one, yes, but still a comet, formed in some distant star system under unfamiliar conditions. It's been baked by cosmic rays during its journey through the emptiness between stars, which changed its chemistry and the way it looks. That cosmic ray processing idea covers most of the anomalies. It explains the weirdness without reaching for anything too wild. Here, how it works. Galactic cosmic rays, those supercharged particles flying through space at nearly light speed, are everywhere out there. They're mostly protons and atomic nuclei, shot out by supernovas and other violent cosmic events. Anything moving through interstellar space gets hammered by them. The rays slam into surfaces, break apart chemical bonds, shuffle molecules, and drive strange chemistry that just doesn't happen in the deep cold of space. Over millions or even billions of years, this radiation changes the surface, building up a crust that can be centimeters or even meters thick, depending on how long and how hard it's been exposed. So, an object like 3IATLAS, probably wandering the galaxy for longer than our solar systems even existed, would be absolutely steeped in cosmic radiation. Its outer layers are different, chemically aged and altered in ways you never see in solar system comets. When it finally comes close to our sun and starts venting gas, what we're looking at isn't its original material. We're seeing the aftereffects of that long, lonely journey, a surface shaped by radiation, crust processed by cosmic rays, releasing gases that may have formed along the way. That's a sharp explanation, simple, but it covers a lot. You can actually test it, at least in theory, by digging into spectroscopic data and comparing what you see to what the radiation chemistry models predict. It's nice because it doesn't lean on anything wild or out there. Just physics we already know, applied to an object whose past we can piece together from its path and what it's made of. This idea explains why there's so much carbon dioxide. Radiation can turn carbon monoxide into carbon dioxide when high-energy particles hit it. It even lines up with that weird polarization signal. If radiation changes the surface, it could mess with how the ice reflects light compared to untouched stuff from our own solar system. And it gives a pretty solid reason for why the surface might scatter light in unexpected ways. After all, if it's been battered for ages, that's going to change the texture and what it's made of. Still, the cosmic ray processing story, as convincing as it sounds, and as much as lab experiments back it up, isn't perfect. People who work on this stuff are honest about the gaps. Sure, it fits the chemistry and how the thing plays with light. It offers good reasons for what we actually measure, both in terms of molecules and light scattering, but it runs into trouble with structure. The organized look you see in amateur photos, those patterns don't really fit with what you'd expect from a surface just randomly roughed up by radiation. Then there's the orbit. The path is oddly precise, not as scattered as you'd think if random outgassing were pushing it around. And the biggest puzzle, why do the amateur photos look so different from the sharp, official telescope images? Is it all just a trick of the camera and some creative processing? Or is there something real there, something that pro instruments miss or gloss over when they clean up their data? Nobody's nailed that down yet. A bunch of research teams have tried to copy what the amateurs see, using big telescopes, careful calibration, and different processing tricks to see if they can get the same structure to show up. Honestly, it's been frustrating. Most of the time, the images just look like the usual fuzzy blobs. Sometimes there are hints of structure, but nothing as bold or clear as the amateur shots. Maybe it's just the geometry. Earth, Sun, and Comet always shifting relative to each other, making features pop in and out. Maybe certain ways of processing images pull out faint but real details while others hide them. Or maybe it's all just noise. Patterns our brains and algorithms invent when they try too hard to find something that isn't really there. So the ambiguity lingers. No one managed to confirm the amateur sightings in a controlled way, and no one's totally ruled out the idea that they're just artifacts either. We're stuck in the middle, not quite sure what to believe. It's unsettling, knowing the data is out there but not really knowing what to make of it. It hangs around the edges of every conversation, even when nobody brings it up. And here's what really bothers people at NASA. It's not aliens or spaceships. No one at the agency seriously thinks 3IATLAS is built by extraterrestrials. The real worry runs deeper. It's about how much we actually know or how much we think we know. Even with all these incredible telescopes, Hubble, James Webb, giant arrays on the ground, able to see tiny things from millions of kilometers away, we still might be missing stuff. Sometimes. We might be blind to signals that don't fit our expectations, just because our tools are tuned to spot what we already believe is out there and quietly ignore the rest as noise. And that's a tough pill to swallow. Confirmation bias sneaks into science whether we like it or not. You set out to build an instrument with a clear goal, calibrate it to spot what you expect, stuff theory and past data already hint at. Then you set up your data processing to highlight those expected signals, brushing off anything that doesn't fit the mold as noise. So when something truly new pops up, something your templates don't cover, your system might just smooth it over, average it out, or write it off as a glitch. Not because anyone meant to, but because the whole setup is built to see what we already believe is out there. That's the worry. You start to ask, what if we're missing entire categories of phenomena just because our tools aren't tuned to notice them? It's not about aliens. It's about being blind to things we never even thought to look for. And then there's the whole institutional mess that comes with public science. NASA runs on public money, so everything it does gets picked apart by Congress, the media, and anyone with a social media account. They have to walk this tightrope, be open about what they're doing, but not so open that every oddball finding gets twisted into clickbait or conspiracy fodder. Imagine a NASA scientist admitting, some of this 3IATLAS data confuses us. It doesn't fit our models. Within hours, you'd see headlines screaming, NASA admits alien probe in the solar system. The careful scientific nuance gets lost. People get confused, trust in science takes a hit, and suddenly you've got a misinformation circus on your hands, so they play it safe. Stick to what's solid. Don't hype the unknowns, instead call them exciting avenues for future research. Highlight the stuff that fits the models. If 3IATLAS looks like a comet, say so. It's not about hiding the truth. It's about keeping things credible and avoiding unnecessary chaos. But this approach creates a gap. The real, messy questions scientists are asking each other in private never make it to the press releases. The public story always lags behind the actual scientific conversation. Scientists studying 3IATLAS actually have piles of data you haven't seen. There are observations still being picked over, numbers that don't have final error bars, early results that might change with more analysis. That's just how science works. You don't rush to publish until you're sure, until you've checked and double-checked, until you know your results hold up. But it means there's always a delay. By the time something finally shows up in a journal, the researchers are already off chasing the next anomaly, the next weird bit of data. The official findings always feel a little behind because the real action is already somewhere else. Right now, behind the scenes, in emails, on video calls, in quick chats at conferences, the conversations sound a lot different than what you see in published papers. People are less sure. They're willing to toss around weird ideas, to poke at uncomfortable questions that would never make it into a formal abstract. The tone is hushed, curious, a little on edge. What if we're missing real features because our data pipelines smooth things out too much? What if amateur astronomers are picking up signals that the big, expensive instruments accidentally filter away? What if that uncanny trajectory precision isn't just luck, but hints at something about interstellar objects we honestly don't get yet? These questions drift through the community. Everyone knows them, but nobody's eager to say them out loud. They linger, never fully answered, never fully dismissed, because the data just won't settle the debate. So here we are, stuck in this useful kind of uncertainty. It's the mess that keeps science moving, but it drives anyone hungry for clear answers totally nuts. Officially, 3IATLAS is just another interstellar comet. The weird stuff, still just research fodder, not the kind of mystery that blows up the textbooks. The trajectory more or less obeys physics, even if some numbers don't quite add up. NASA's still watching it closely, and every press release insists nothing wild is happening. All of that could be true. Or maybe there's something huge we're all missing, something we'll only notice when it's way too late, when the comet fades away, taking whatever secrets it had back into the dark between the stars, far beyond anything we could ever chase. And the clock's ticking. Every day, 3IATLAS slips farther from Earth, gets dimmer, harder to spot. The window for answers is closing fast. Every last observation feels heavier because we know we're running out of time. This could be it, the only shot we get, not just in our lives, but maybe for our whole era. One chance to study something that wandered who knows how far to pass by us, then vanish forever. If there's something we're missing, some pattern buried in the noise, we won't realize it until years from now when it's far too late. That idea that we might be watching something truly new and not even seeing it because we're stuck in old ways of thinking, that's what keeps some folks at NASA glued to their screens long after midnight. They're still running numbers, still doubting what they thought they knew about comets, still worrying that the universe is always a step ahead. Interstellar visitors are a brand new story for humanity. Before 2017, we'd never confirmed even one object from outside our solar system passing through our neighborhood. Not one. Theorists guessed they should be out there. Models said planets throw out debris as they form, and some of it should wander the galaxy, bumping into other star systems. But guesses and proof aren't the same thing. For all of history until just a few years ago, interstellar visitors were only numbers on paper, possibilities, not realities. Oumuamua showed up out of nowhere like the universe threw us a curveball just to see what we'd do. It was October 2017. The Pan-STARRS telescope in Hawaii picked up something odd, moving through the inner solar system on a path that made one thing crystal clear: it didn't come from around here. This thing wasn't tied to our sun, not even a little. Interstellar. No question. Astronomers scrambled. For a brief window, they watched as much as they could before it slipped away forever. And honestly, nothing about Oumuamua made sense. Not even close. First off, it wasn't shaped like anything we'd seen before. It was long, way longer than it was wide. People compared it to a cigar, but that doesn't even do it justice. It was also shiny, which usually means ice or metal, but then it didn't act like a comet at all. No tail, no coma, none of the gas jets you'd expect when the sun heats up a chunk of ice. And then, just to make things weirder, it sped up as it left the sun. Gravity couldn't explain that. Something pushed it, but there was no blast of gas, no visible jet. The data just refused to cooperate with any of the usual explanations. That's when Avi Loeb, a Harvard astronomer known for thinking outside the box, threw out a wild idea, one that honestly fit better than anything else. What if Oumuamua was artificial? Not a rock or a chunk of ice, but a thin piece of tech, like a light sail propelled by sunlight. Maybe it was a probe from an alien civilization. Maybe it was just space junk from some forgotten craft drifting through the galaxy. The suggestion lit a fire under the community. Headlines, arguments, fierce debates. Most astronomers pushed back. They insisted on natural explanations, even if those ideas felt like a stretch. Some talked about hydrogen icebergs or slabs of nitrogen from distant Pluto-like worlds. None of those theories really fit, but anything seemed better than aliens, at least without hard proof. 5 years later, the mystery still stands. We have the data. The measurements are real. But the story you tell about Oumuamua depends on what you think is possible. Some researchers say it was just a weird natural object, a cosmic oddball, but nothing out of bounds. Others keep the artificial idea alive. No one has shut the case for good. It's a reminder that sometimes the universe hands us something that doesn't fit our usual boxes, and we just have to live with the uncertainty. Then in 2019, along came 2I/Borisov. This time, everyone exhaled. Finally, an interstellar visitor that played by the rules. It had a classic comet tail, a visible coma, and the kind of outgassing you'd expect as it warmed up near the sun. Spectra showed familiar stuff: water ice, carbon monoxide, matching what we see in our own solar system's comets. With Borisov, it felt like things made sense again. Most interstellar objects, it turns out, are probably just icy wanderers, kicked out of their home systems during planet formation. Drifting until they cross our path. Nothing weird. No wild theories needed. Science could get back to business as usual. For now, the universe seemed normal again. Now we've got 3IATLAS, and somehow it manages to feel even stranger than Oumuamua, even though on the surface it looks more like a normal comet. It's got a coma, there's clear activity, spectroscopy picks up outgassing, and you can see the start of a tail as sunlight pushes dust away from its nucleus. By all the basic checks, this thing is a comet. But then you dig into the details, and things just don't add up. The path it follows is almost too perfect. The timing of its acceleration is suspiciously precise. Its makeup is way out on the edge of what we expect. And when amateurs look at it, the whole structure seems weirdly organized. It's almost like someone took notes after Oumuamua, realized that weirdness attracts too much attention, and decided to make the next probe look just enough like a comet to slip under the radar, but still do whatever it came here to do. Yeah, I know, that sounds a little out there, paranoid even. The sort of thing peer-reviewed journals roll their eyes at. But when you're staring at possible first hints of alien technology, even if that's a long shot, a little paranoia doesn't feel crazy. Maybe we shouldn't be so quick to brush off the stuff that doesn't fit. Science is scrambling to keep up. The way we think about these objects is changing fast because interstellar visitor isn't just a thought experiment anymore. It's something we can actually see and try to explain. Take the light sail idea. It's not just about Oumuamua now. More and more researchers are digging into the physics of thin films, materials just a few microns thick, getting pushed across the void by sunlight. Turns out the math works. No engines, no fuel. Just spread out a huge surface, keep it light, and wait. Send 1,000 of these sails off to nearby stars. Some will make it. Most honestly won't. They'll hit dust, get zapped by stars, or tossed out by gravity. But a handful will survive, and after an almost unimaginable amount of time, they'll reach other systems, open up their instruments, and start collecting data. There's also the idea of hollow probes, shells instead of solid blocks. You get way more surface area for less mass, so they're easier to push to those wild speeds. They're also sneakier, harder to spot since they don't bounce back much light. Plus, they might be better at catching solar energy or shedding heat. Some folks are even kicking around the thought of fractal shapes, where the same patterns repeat at different sizes, cramming a massive surface area into a small space. That could help with energy collection or cooling. Sure, these ideas are out there. They're not proven, just sharp what-ifs. But the physics checks out, and the engineering is stuff we can mess around with in labs right now. If we wanted to send probes to other stars using today's tech, these are the designs we'd likely build. Not giant rocket ships with crews, not slow-moving arcs, but nimble, lightweight robots riding light or other clever propulsion tricks that don't need fuel tanks the size of office buildings. And if these ideas make sense for us, odds are they make sense for others too. Engineering, like evolution, tends to land on similar solutions when faced with the same problems. Then there's the wildest idea, dark visitors. Imagine objects zipping through the solar system, too tiny or too dim for us to notice. We only spot the bright ones, the big ones, or the lucky ones that pass close enough for our telescopes. But what about all the rest? Little dark travelers slipping by in the outer solar system, never crossing a camera's line of sight, unless by sheer luck they block a star or flash in a survey image for a split second. Makes you wonder, how many of these interstellar guests have we missed? How many are flying through right now, completely invisible to us? Honestly, the real number is probably a lot, more than we're comfortable with. Our count of interstellar visitors is almost certainly just the tip of the iceberg. Look at the stats. After Oumuamua, Borisov, and Atlas, scientists ran the numbers. Turns out, there might be dozens or even hundreds of interstellar objects drifting inside Neptune's orbit right now. Most of them are too dim for us to spot. Almost all are cruising along paths that never bring them anywhere near Earth, where our telescopes work best. They slip by, completely unnoticed, and by the time we'd even know to look, they're already gone. That leaves us with a weird, unsettling truth. Space is probably full of these wanderers, and we barely see any of them. Think about it. The galaxy could be swimming with travelers, chunks of rock, bits of ice, maybe even stranger things. Stuff blasted out of billions of planetary systems over cosmic time. We might be wading through a vast, sparse ocean of cosmic debris, and maybe even the odd artifact, but we only notice the brightest, closest, most obvious ones. Avi Loeb isn't shy about speculating on this. He and others have suggested that maybe there's a galactic communication network right under our noses, one we just don't recognize. Not radio signals. We're already listening for those with SETI and similar projects. But something more subtle, using physics we haven't cracked yet. Imagine gravitational waves carrying coded messages through spacetime itself, or neutrino beams passing straight through planets, almost impossible to block. Maybe there's quantum entanglement in play, with information zipping around faster than we can comprehend. Whatever the trick is, those signals could be flooding Earth all the time, but we're just not tuned in. We're using the wrong equipment, like trying to catch Wi-Fi with an old AM radio. The signals are there, the tech is real. You just need the right kind of receiver. Without it, you're completely oblivious, no matter how much is happening all around you. And then there's the whole question of how you'd actually explore the galaxy. Space is huge. Light itself takes years just to get to the next star. Even if you send probes at close to light speed, they'd need decades, centuries, or more to complete their missions. No civilization is going to babysit a robot halfway across the galaxy in real time. You can't send instructions back and forth. By the time you get a reply, the situation's changed, or everybody's moved on. So you build probes that think for themselves, adaptable, independent, able to stick around for thousands of years and just get the job done. Park them in stable spots around stars or big planets. Let them observe, collect data, and wait until something, maybe a faster courier probe, comes by to pick up what they've learned and carry it home. Jupiter, or any big gas giant, is a no-brainer for these kinds of observation posts. If you're searching the galaxy for planets where technology could pop up, you want your probes parked somewhere stable, somewhere with a good view, and somewhere easy to find again. Gas giants fit the bill. They're huge, easy to spot from far away, and their gravity makes them perfect for slingshot maneuvers. Plus, their magnetospheres give your probes plenty of free energy, and their stable regions, like Lagrange points, are great for parking long-term. It's almost like they were made to host long-lived, watchful machines, quietly keeping tabs on the cosmos. Jupiter doesn't stand out in this picture. It's just one of millions of similar spots scattered all over the Milky Way. Each one could easily host its own network of sentinels, assuming there are civilizations out there who care about watching and collecting data. Think about it. A gas giant sitting in or near the habitable zone, big enough to have a strong magnetosphere but not so massive that it messes up the formation of rocky planets closer to the star. That's prime real estate for building observation outposts. From there, you get a clear view of the inner system. Light takes only minutes, not hours, to reach your targets. You're close enough to see everything important, but far enough from the star to dodge nasty flares or dangerous radiation. Plus, the gravitational setup means you can stick around for ages without constantly burning fuel. Some theories suggest that interstellar probes chase after power sources. They head for places where they can recharge and keep running indefinitely. So, stars, soaking up light and turning it into energy, sure. But also magnetospheres, where charged particles and electromagnetic fields make for perfect energy harvesting conditions. There are accretion disks around young stars or dead ones. Planetary radiation belts loaded with high-energy particles. Basically, anywhere you can grab enough power to keep going. If any of this is true, Jupiter isn't just a convenient parking lot in our solar system. It's a recharging hub. A place where probes gather because the physics make it easy to stay powered up. Stretch that idea across the galaxy, and you end up with gas giants everywhere quietly hosting equipment we can't see, networks running in the background while we have no clue they're even there. History actually backs up this idea, and it's a little unsettling. Humans have always looked for the high ground when it comes to watching and gathering intel. Ancient people built watchtowers on mountaintops. These days, we use satellites parked in geosynchronous orbit to keep an eye on things. We put telescopes at Lagrange points because they're stable. We always pick spots that give us the best view for the least risk. If aliens think anything like we do, if evolution drives strategy as much as it drives biology or tech, then Jupiter's Hill sphere is like the ultimate high ground in our solar system. From there, you can see pretty much everything. Anything happening on Earth is visible, with only a short delay from the speed of light, maybe 12 to 40 minutes depending on where everyone is in their orbits. You can listen for radio, watch launches, catch nuclear explosions, even track changes in the atmosphere. And the whole time, you're far enough away that nobody on Earth can reach you or even notice you, especially if you're built to stay hidden. Now picture the galaxy filled with these networks, millions of sentinels spread out over billions of years, watching every star system within reach of whoever set them up. Each one just quietly observing its assigned star, keeping tabs on whatever planets are there, looking for any sign of life or technology. Some are watching systems with nothing but microbes or simple animals. Others are focused on worlds where civilizations are just starting to figure out tools and radio. A handful keep an eye on advanced species who already roam their own star systems. The probes don't mess with anything, at least not obviously. They just watch and record, sending everything back home, building up a huge long-term map of how the galaxy is changing. Which systems might go somewhere, which ones burn out, which make it to the stars, and which never get past the basics. Picture this: probes that only wake up when something big happens. Maybe they're programmed to scan for civilizations that hit certain milestones, like figuring out nuclear weapons, or building radio telescopes to listen for signals out in the cosmos, or even just launching something past their own planet's gravity. Each of these is a flag, proof that a species has moved beyond being just another planetary civilization and is ready to play on the galactic stage. So maybe 3IATLAS is stirring now, sliding closer to Jupiter to get a better look, because we finally crossed one of those lines. Maybe something we did, some experiment, some broadcast, flipped a switch in ancient alien hardware that's been drifting through space since before Earth had continents, since before there was even anything crawling around in our oceans. Of course, this isn't science backed by evidence. It's just a thought experiment, a way to stretch what we know and imagine what might be out there. But it's not pure fantasy. These ideas spring from real physics, just extended into territory we're only starting to explore. And whatever 3IATLAS turns out to be, it's already forced scientists to ask new questions, whether they like it or not. Because if these objects streaking through our solar system are artificial, if we're being cataloged by some ancient network we never even guessed existed, then everything changes. Our spot in the universe shifts. What we think about intelligence, about civilization, about being unique or alone, it all gets shaken up. Suddenly, we have to face the possibility we were never really alone, never all that special, just too primitive to notice we were being watched until our tech finally caught up and caught a glimpse. Astronomy's gone through a wild transformation over the last decade. The tech has exploded. Now we can see more and process it way faster. Artificial intelligence is right at the heart of it, turning the whole field on its head. Machines are spotting patterns we'd never catch, pulling signals out of the noise that would look like random static to us. Sometimes, what they find makes things like 3IATLAS seem almost simple. The universe is stranger and more complicated than any of our old theories prepared us for. Funny thing is, this revolution didn't start with a bang. Like most big shifts, it crept in, quietly building up momentum. Astronomers have been using computers to crunch telescope data for ages, nothing new there. But now, with deep neural networks and mountains of data, AI isn't just working faster, it's working differently. These systems pick up on patterns no human would ever spot, even after years of staring at the data. Train an AI on millions of stars, and it doesn't just sort them by brightness or color like we told it. It finds the oddballs, the stars and events that don't fit any box, the flashes too faint or too quick for our old methods to catch. Suddenly, we're not just seeing more, we're seeing differently, and sometimes that's all it takes to change everything. Microflares are a great example of stuff we've always missed, until AI came along and showed us they were hiding in plain sight. These things are tiny, just brief flashes in stars or other objects, sometimes gone in less than a second. Even though they release as much energy as a small nuclear bomb, it's all spread out over wavelengths that make them pretty much invisible unless you have the right gear and some serious analysis tools dialed in for fast, fleeting events. For years, everyone assumed microflares were rare, mostly because, well, we never saw them. Classic case of seeing what you expect, not what's really there. Turns out, we just weren't looking the right way or crunching the data with methods sharp enough to catch these things. Now, with AI running the telescopes, microflares show up everywhere, thousands every night in all sky surveys. Nobody really knows what they all mean. Some are probably just regular star stuff, magnetic reconnection, small-scale flares, stuff like that. Some might be starquakes, shakes in the star's guts that cause quick bursts of light. But a few don't fit any of the usual categories. Their energy patterns or timing just don't line up with known physics, so they sit in the data, waiting for someone to figure out what's going on. Microlensing events are even weirder, and AI's made it clear just how common they actually are. These happen when something massive drifts between us and a far-off star, and its gravity bends the light so the star briefly brightens. That's general relativity in action, proven again and again, and it's how astronomers find exoplanets and dark matter candidates, just by watching stars and waiting for them to flicker in the right way. But now, AI's picking up microlensing events sparked by objects way too small to be planets, way too dark to spot directly, and moving at speeds that don't really match anything we know in the solar system or the galaxy. Some of these events only last for a blink, milliseconds, really, barely enough to show up in more than one image. Some have weird, lopsided brightness curves, like the thing doing the lensing isn't even close to round. And a few are downright unsettling. Researchers talk about them behind closed doors, but officially they just get dumped in the anomaly bin, waiting for someone to take another look. But since these events never repeat, nobody can really follow up. Then there are the transients, the real Wild West of astronomy right now, thanks to AI. These are things that pop up in telescope images for maybe a frame or two, then vanish. Could be gone in minutes or hours, moving on or just fatting away below what we can see. Before AI, most of these were lost because nobody could sift through every single image from every telescope, checking every faint dot to see if it was real or just noise. A person might check a few targets a night, maybe a few hundred images if they really hustled. AI, it chews through millions of images in the time you'd spend on one, and suddenly, transients are everywhere. Most are just asteroids, satellites, or known objects doing their thing. Some are cosmic rays fooling the detectors. But once in a while, something moves across the sky like a real object, with a path and speed that grab attention. Sometimes, those numbers just don't add up and the astronomers lean in for a closer look. And now, with the next generation of telescopes coming online, things are only getting crazier. The Vera Rubin Observatory in Chile, once it's running at full tilt, will image the whole sky every few nights with this monster camera. Over 3 billion pixels, churning out 15 terabytes of data every night. That's a mountain of information that needs to be processed, calibrated, and picked apart. Over 10 years, it'll map the southern sky hundreds of times, basically making a time-lapse movie of the universe. You'll see everything: asteroids tracked across the sky, comets caught on their journey in and out, supernovae exploding and fatting, variable stars poolsing in and out of brightness. All of it cataloged automatically by AI, searching for the rare and weird among oceans of data that would have totally overwhelmed old-school analysis. The haystack's bigger than ever, but now we've got machines that can actually find the needles. The Euclid Space Telescope is out there, mapping the universe's shape and tracking how dark energy sculpts the cosmic web. At the same time, it's grabbing snapshots of everything that moves or changes in its view, logging massive catalogs of solar system objects, all from a spot in space where there's none of Earth's atmospheric fuzziness. Then there's the Nancy Grace Roman Space Telescope, getting ready for launch soon. It's going to run microlensing surveys that are way more sensitive than anything we've tried before. We're talking about finding exoplanets through gravitational lensing at distances and sizes that current tools just can't handle. And along the way, it'll stumble onto all sorts of other weird, fleeting events as well. All this data gets fed into AI systems built to sniff out the oddballs, the stuff that doesn't fit, the one-in-a-generation anomalies like 3IATLAS. And honestly, these systems are blowing past what people thought was possible. They're churning out discovery lists so fast that human astronomers just can't keep up. Now, researchers have to triage, picking out only the most interesting or bizarre things to follow up on. But here, where things get awkward, the part people rarely say out loud, some teams are spotting things they're not publishing. No, it's not some conspiracy. It's just that sometimes the data is so strange, so far from anything expected, that putting it out there without more evidence feels reckless. And getting more evidence is tough when you're chasing things that show up once, then vanish before anyone can get a second look. Careers can tank if you go public with claims that can't be backed up, or if it turns out your discovery was just a glitch or a software hiccup. So when an AI flags something truly bizarre, a microflare in an empty patch of sky, or a transient streaking across the outer solar system at 2% the speed of light, or some lensing event pointing to an object with mass that just doesn't make sense, researchers hold back. They wait for backup from other telescopes. They check and recheck their instruments. They talk quietly with colleagues they trust. The anomaly just sits in a database, unannounced and unexplained, maybe gathering enough siblings over time to finally get published, or maybe just sitting there forever, in limbo. There's also this low-key buzz among astronomers about fast movers. These are objects caught by multiple telescopes, moving too fast to be regular solar system stuff, but not fast enough to be coming in from interstellar space. They're in this weird in-between, speeds that don't really add up unless you imagine some oddball orbit. Some people figure these are just secret satellites or space junk from military launches nobody talks about. But not everyone buys that, especially when these objects flicker in ways that suggest they're tumbling or oddly shaped, nothing like the satellites we know, or when they pop up in spots where it'd be a real stretch for human tech to get them there. And then there's the reflectance curve mystery that AI keeps flagging. Most space rocks reflect light in ways that match what they're made of. Asteroids, comets, whatever. They've all got their signature shine. But sometimes, AI picks out something that just doesn't fit. Maybe it's reflecting light almost too perfectly, like it's got a surface polished smooth at the microscopic level, or it's bouncing light in a way that natural objects just don't. Sure, it could be a glitch, or maybe some weird mineral we haven't cataloged, or just the way the instruments read the light. Or maybe it's something totally outside what we expect, some kind of material or structure we just haven't thought about when we picture what's floating around out there. Timing matters more than most people realize. 3IATLAS showed up right as our ability to observe the universe exploded, and AI handed us tools we couldn't even imagine 5 years ago. Suddenly, we're picking up things we never saw, transients too faint for humans, microlensing events that vanish in minutes, weird outliers buried in mountains of data. And honestly, what we're seeing doesn't quite fit the old idea that every interstellar visitor or solar system object is just a rock following the laws of physics. Maybe it's just the universe being its usual bizarre self. Bigger telescopes, more edge cases, stranger stuff at the boundaries of what we understand. But there's another way to look at it, and this one is a little harder to shake off. What if we're not seeing new phenomena that just started happening? What if these things have always been here, events and objects all around us, hiding in plain sight until our machines got smart enough to spot them? Algorithms now pick up patterns no human ever could. The galaxy might have been full of these travelers for ages and we just never noticed. Now, if 3IATLAS is doing something on purpose, like dropping probes near Jupiter while we watch, or if it's part of a bigger plan, then you have to wonder, is it alone? Or are there more out there? Networks operating quietly, invisible until our AI-powered systems started catching glimpses through microlensing and those odd, fleeting transients. Every weird detection, every flash that doesn't make sense, might be a clue, evidence of something or someone we're only just now learning to see. And here,